Hi there, in this video I want to quickly show the repair of this monster, the HP5334B universal counter and the latest addition to my lab. As you can see, HP did not spare buttons here. Its front seems just to go on and on. Actually, this is its biggest drawback. The unit is meant for mounting in a 19-inch rack and absolutely enormous in length and depth compared to standalone counters. The height, on the other hand, is a relative moderate 2 rack units or about 88 mm. The whole thing just about fills my bench. When the unit arrived, fresh from eBay, I checked the voltage setting on the rear first, which was correct for the UK mains, and then powered it on. The unit came to life and passed the self-test. Unfortunately, I did not have the camera rolling because about 5 minutes later I heard a loud popping and sizzling inside and the display went dark. Instead of counting, the unit released copious amount of very smelly magic smoke. I managed to get the cover off without too much trouble, and the inside looked surprisingly clean for an almost 30-year-old device, but then it has no fans that would suck in dust. Everything except the front panel is on a single huge PCB and all through hole as you would expect. A first look for skid marks, burns or even soot residue did not show anything until my eye fell on this capacitor on the left. That certainly did not look quite right. An exploded reefer cap. Again, because when I got my Solartron 7150 Plus multimeter, it had the same issue, but in this case the reefer cap was encapsulated in a filter. I leave a reference to the video on that part of the Solartron restoration in the description. Comparing the board with the component layout from the HP5334B service manual, which I downloaded from the internet, it is clear that before its violent death, the capacitor was going by the name of C207. And a look into the schematics shows its role as an X2 mains power filter capacitor. Its safety category is X because it's across live and neutral. The 2 means it's tested to 2500 volts. An X capacitor can fail either open or short. If it fails open, the filtering is lost. If it fails short, as in this case, it blows the fuse. In either case, the user and the equipment is not endangered. Interestingly, C210 is an identical reefer capacitor, also across live and neutral, and it's still working. Moreover, C208 and C209 are also reefer capacitors, but only 2200 picofarad and of safety category Y2. The Y means they are to be used between live and ground, or neutral and ground. Y capacitors should always fail open because if they fail short, the chassis would become live, causing a shock hazard. So we have a total of 4 reefer capacitors here, of which 1 has blown up. It is obviously just a matter of time for the others to follow, which means I will replace all 4 of them. Unfortunately, this means I have to get that huge PCB out to be able to replace the caps, and that's no small task as this exploded view shows. I basically have to remove all components from the rear panel, remove the transformer, and disassemble and remove the front section as well to free the PCB so it can be pulled out towards the front. On the rear, this means taking these secondary B and C inputs out, removing the transformer and the heat sinks for the voltage regulators. On the front, it's slightly easier as it basically means removing the nuts on the front B and C connectors and the screws holding the front panel to the side panels. Electrically, the whole front panel is simply plugged into the main board using this edge connector in the upper right. This massive board was so awkward on my small bench that I could not work on it and give the camera a decent view, so this still is kind of the only decent image from the undertaking. You see the front is removed, the transformer is gone, and the rear panel is stripped. I put the 3 connectors with the attached cables into a plastic bag with some tissue for cushioning because the other ends of the cables are still soldered into the board and I didn't want the cables and connectors to go flapping in the breeze, as Dave from EEV blog always says, when I turn the PCB around to solder the caps. This is a view of the repair. The two black capacitors are 100 nanofarad Panasonic metallized polyester film types, rated X2. The two white capacitors are again RIFA types, but brand new ones made by KEMET. I'd like to avoid using RIFAs, or rather metallized paper caps, but I could not find suitable through-hole caps of the needed values, class and voltage rating. Well, if they last again 30 years or so, I don't really mind too much, and it might give a new generation of electronic enthusiasts their moment of RIFA madness. So what's wrong with these capacitors? Here's a close-up of the exploded one, and you can see that the encapsulating resin has lots of cracks. This is not a consequence of the explosion, but the cause of it. One article I read explains that the resin's thermal expansion rate does not match the expansion of the actual capacitors inside, which means stress at every temperature cycle, and over time hairline cracks develop that let moisture in. That moisture lowers the resistance, so the capacitor heats up, turning the moisture into steam, and the pressure destroys the capacitor. Here you can see how the pressure has bulged out the capacitor, shredding the resin and exposing the actual metallized paper foil. This is the identical unexploded capacitor for comparison, and you can see it also has lots of hairline cracks already. So if you see capacitors with these cracks, it's high time to replace them. Even the 2200 picofarad Y capacitors show these cracks already, although they are a bit harder to see. It needs the light to come in at the right angle to make them visible. And here's one of the brand new replacement RIFA capacitors. So far all is good, and I really hope over the last 30 years the manufacturers have learned their lesson and avoided making the same mistake. It is interesting that the capacitance of a cracked but not yet exploded capacitor measures high. It is supposed to be only 100 nanofarad. This is because the moisture inside lowers the resistance, so it's slightly leaking. Most multimeters measure capacitance by charging the capacitor with a constant current for a specific time and then measure the resulting voltage. A leaky capacitor has less voltage than a good one, but for the meter it behaves like a bigger capacitor, which would charge slower and therefore also accumulate less voltage in the specified time. You can see this even with a normal multimeter measuring the resistance. Both capacitors have the same capacitance, but the old RIFA one takes much longer before it has accumulated enough charge for the meter to read overload resistance. If your meter can measure conductance, you can get an idea what the resistance is. The good one measures 0.002 nanosiemens, which is as low as the BM869S can go, and equivalent of 500 gigaohms. The unexploded RIFA takes a while, but it settles on 0.56 nanosiemens or 1.8 gigaohms. That is still quite high, of course, and explains why I could not make it explode for the camera. Trying it many times and even soaking it in water left it completely unimpressed. And the smaller RIFA was equally resilient. Well, I had planned this video to contain the second RIFA's demise, so here it is, even if the voltage is about 100 times higher than mains, thanks to a neon transformer. Enjoy the show! To wrap things up, I mentioned already that this counter was a rack mount. What it did not have was feet, which are normally part of the unit, but they have been removed and then lost. The thing is, if you use the counter standing on a shelf, it needs feet to allow airflow from the bottom. I looked on eBay and replacement feet are crazy expensive for a simple piece of plastic. Since I had the board out, I used the existing holes in the bottom plate to put small screws into 4 pieces of wood and then put self-adhesive little rubber feet on those. This is not very elegant but functional and pretty much invisible during operation. after replacing the fuse as well, the moment of truth. Yeah, it passes its self-test and is working without smoke. The dashes are the HP5334's ways of saying that there's no input signal. Here's the counter in action, measuring a 10 MHz signal from my function generator on channel B. It is pretty much spot on after 30 minutes of warming up of both the counter and the function generator. For comparison, my GPS disciplined oscillator set to 10 MHz on channel A. The counter is just 0.7 Hz off. The display on the HP5334B is in engineering notation, so what you see is 10.00 something times 10 to the power of 6. My model only has the standard crystal reference, and from the CAL sticker I found, it was last calibrated in January 2003. Pretty good. If I need more accuracy, I can simply use my GPS-DO as an external time reference. If you like this video, consider subscribing to see more and maybe becoming a Patreon. Link in the description. As a Patreon, you get early access to videos, a blog, and other exclusive content. Thanks for watching.